All right, welcome y'all. So today we're going to learn about IMFs or intermolecular forces. But before we do so, I want to talk really quick about intramolecular forces. So if we look at one of my favorite molecules, water, we actually have our intramoleculars. So intra meaning inside, molecular referring to the molecule. So our intramolecular forces are our hydrogen covalent bonds right here, our covalent bonds. Intramolecular forces are what holds the atom together, and these are pretty darn strong. But the question becomes, in water, water isn't one big continuous molecule, it's a whole bunch of small individual molecules, like this one right here, held together to other small individual molecules. So if I take another little OH, what holds these two molecules together? What is this invisible force holding them together? Well, that's what today's lesson is all about. Today's lesson is about intermolecular forces. I'm going to highlight that for extra effect. So today we're talking about intermolecular forces. That's our IMF. Now, inter referring to in between our molecules. So these are the forces that hold these molecules together. And there's a bunch of different kinds. We're going to be learning about a few, but before we really do, I just want to say one thing, that inter is weaker than, let's switch up the color, than intra. Inter is weaker than intra. So if you're pulling two water molecules, they're not going to split apart into individual atoms. They'll just come apart themselves. So that's just a little key point we want to shove off to the side over there. Just keep it in mind for when we're talking about the specific properties that come with IMFs. So as we talk about intermolecular forces, we want to think back to, and actually I'm going to go back to water. We want to think about our dipole moments. So in water, we have a dipole moment going from the hydrogen to the oxygen, meaning the hydrogen is going to be slightly positive. The oxygen is going to be slightly negative. And this is due to the fact that oxygen has a higher electronegativity. Oxygen has a higher electronegativity. Therefore, it's more partially negative. And because of this dipole moment, we actually see that the molecule has this kind of negative side up here and this positive side down here. And what happens is when we get another water molecule come right up to it, this one's also negative to the hydrogen positive. We start to feel this force of attraction. So we feel this attractive force. And that can be described by our Coulombic forces. Basically, when you have two charges that are of opposite charge, they attract, just like two charges of the same charge repel. So the positive hydrogen end attracts the negative oxygen end and holds these molecules together. That is one example of IMF. In fact, that's our first example of IMF. We're going to talk about three. So number one, we have hydrogen bonding. Now, this only happens when we have molecules that have hydrogen bonded to nitrogen, oxygen, or fluorine. Now, it's really specific then, hydrogen bonding. We need to have hydrogen bonded to fluorine, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen. So we must have hydrogen bonded to one of these three elements. Now, if we take a quick look at the periodic table, we can kind of see why. Just going to move that guy over here. Nitrogen, oxygen, and fluorine are three of the most electronegative elements there are. And when they bond with hydrogen, the least, not the least, but one of the least nonmetals, you see that it creates such a large difference in electronegativity. In fact, the difference in electronegativity, to just shorten it, is so large, the partial, I'm going to move this diagram, and I'm going to try and not move these, is so large, the partial charges become really large as well. Basically, all I'm saying right here is that because the electrons are pulled so violently towards the more electronegative atom, we get a really large partial positive on the hydrogen and a really large partial negative on these other elements. So this is important because if we have a larger charge, we have a larger force. Therefore, hydrogen bonding is also the strongest IMF, the strongest intermolecular force. So we're going to go down to our next one, number 2, dipole bonding. And you guessed it, this happens between two dipoles. So if we look at H2S, oh, I wrote H2O, my bad, H2S. It's the same structure as H2O, except now we have sulfur, which sulfur has a considerably smaller electronegativity at 2.54 or 58 compared to oxygen's. So this is going to form a dipole, same as H2O, except it's going to be weaker. So the partial positive here is so much smaller than that of water. And the partial negative is so much smaller than that of water. So while this is very similar to hydrogen bonding, this one doesn't need hydrogen. It just needs any dipole. And second, this overall force is going to be weaker. So this dipole force or bond is weaker than hydrogen bonding. So it's just overall going to be weaker, but it's the same concept. And it works with any dipole. It doesn't have to involve hydrogen. Another quick example of this is if I have, let's say OS, oxygen and sulfur. Once again, sulfur has a lower electronegativity. So sulfur is going to become partially positive. Oxygen is going to become partially negative. And if we have another OS right next to it, we're going to get a dipole-dipole. So anywhere where we have a dipole moment represented by our vectors, we will have a dipole-dipole bond possibility almost. All right, so finally, on to our last one, number 3. This is called London dispersion forces, also known as LDFs. There's also another name, Van der Waals, and I hope I spelled that right. I may not have. And unlike the first two, which dipole-dipole bonding happens in polar molecules only, and same as hydrogen bonding, it's going to be polar. London dispersion forces happen in anything, polar or nonpolar. The only requirement is that something needs electrons. So one of the things we can look at is we'll go ahead and look at neon. If we look at an atom of neon, we've got plus 10 in the nucleus, and then we have our electron cloud. The thing about electrons is they kind of move pretty freely within their orbits. Let me just see if I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. But the thing is, because electrons move, sometimes we can have most of our electrons on one side of the atom. So we can see that all of our electrons actually, or most of them, are ending up on the left side of the atom. And when this happens, the atom itself actually gets a small dipole moment where part of the atom is slightly positive and part of the atom is slightly negative because we have more electrons on the negative side and less electrons on the positive side. And due to this, we get this ability to bond. If we have another neon close by, and I'm actually just going to go ahead and copy this one. I'll copy the whole thing. This positive and this negative end can feel this attractive force. And right here we have our LDFs, our London dispersion forces. And the thing about this is that the more, I'm going to highlight that, more electrons, the stronger the force. And with that said, that can just be explained by if we take a look at maybe argon with 18. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. With more electrons, the partially negative side has more electrons to make it negative, and the partially positive side has more of a force from the nucleus to make it positive. So we have a stronger force. It's literally just adding it up and kind of looking at it in a logical format. So with that said, I just want to conclude on one final note. Our IMFs from strongest to weakest are going to be H bonds, hydrogen bonds, then dipole, dipole, then LDFs. So have a great day. I hope this helped, and